Okay, so this will be the final video on the condensation homework. I'll go over my solution and some results I found, and go over the code in detail. This is a very finicky simulation, especially even if you get it working right. There's still some caveats. It's very delicate. So the first thing I did before I started finishing up the code base that I gave you the template for yesterday is I just looked at what I should get. So here is what my intended inputs are. I have the number of random walkers, my radius of that absorbing sphere, how many absorbing spheres I had, their volume equivalent radius here, the size of my space, and then I get my C infinity. And then this is the theoretical steady state concentration. This is my C infinity in the top black line. And this is the size of our system, right? This is from 0 to 200, which is my outer radius. And it's right there at 0 is around 6. So that makes sense. But you see there's a little gap here. Well, remember that in our simulation, we're always feeding, we're always having the n number of random walkers in the system. So C globally will be the C infinity. But so if you don't reach C infinity out here, see there's that gap there, then there's probably no chance that your actual steady state concentration that you measure in simulation will be the same to the theoretical because there's this gap here. So if you make it bigger, let's say, let me get 50. So the depletion zone is huge, right? So there's this giant gap here. Now, when you run the simulation, it's always going to be this, your C infinity here, your concentration is always going to be C infinity out in this, because you keep having boundary conditions, recast, absorb walkers out there. So you're never going to reach that steady state. You're always going to be coming back, touching this. So this ain't going to work. But if you do something very small, like 1, okay, yeah, you can reach steady state, but there's so much noise here that you won't even see the difference between your steady concentration and the steady state. And it'll take forever to get there because it's such a small absorbing sphere in the middle. So you got to kind of guess 5, 6. Yeah, that should get you there. Or you could extend your system out to say 500, and you should be good. But then you have to be careful because your initial concentration will be very, very small. So you might need to make it 10 million to get it up there. And I'll show you how this runs in a minute. Like 5 million actually didn't take up that much memory. It ran up pretty good, but it was a little slow. You'd have to run it for several hours. So let's go back. I sent you a template. We talked about this a while ago, where this is basically a code plan, where we have our main file here. We say, okay, I'm going to initialize my arrays. I have my definitions here, number of random walkers, what time I want to go to, my space. Definitely want to go more than 100 here. Your size of your absorbing sphere, all this is tunable, and then your DR for your shells for concentration and define phi. You'll see in my final code these will be different. I even add some, but it's basically a template. You can work off of it. It's not set in stone. You can add and subtract. I also just gave you an outline for the main part, and I suggested that you do everything as much as possible in functions. So if you have a task, write functions for discrete tasks. Initialization a task that we do in the beginning. Just do all that code in one function. That way it makes the main look better. It also helps decoding. Helps decoding a lot. A code base like this is going to take, a project like this is going to take a lot of decoding. You're probably going to spend more time decoding than actual writing the code. For example, every year when I teach this, I also do the coding again myself. So this has been the 4th or 5th time I've actually coded the simulation. Even I took a little while to decode. I had to decode it, debug it a lot. I mean, debug. That's what I said. Debug. I had to do a lot of debugging. things like, am my initialization right? Like you might have an error here in your concentration, but that error could be because you initialized your random walkers wrong, and they're in positions you don't expect. And then when you do define your concentration, the bins you're putting in your random walkers are actually bigger than the length of your concentration array, and then that causes a seg fault or something like that. So something that happens in the beginning could affect the code all the way at the end. And if you're like, oh, I get to the concentration, my concentration doesn't make sense. Well, where did I make the mistake? Did I make the mistake in the moving of the walkers? Did I make the mistake in the recasting when they get absorbed? Did I make the mistake in the periodic boundary condition? Am I measuring concentration right? That's why it's very important to have these all in discrete things. You can see what's happening. Like, oh, let's test this. Well, I'll print all the coordinates of my random walkers after initialization, or at least the radiuses. And then I'll feel, okay, I maybe print, and I say, oh, that's fine. And then I erase that code and say, okay, let's print all the positions of the radiuses of the recast walkers or the periodic boundary condition walkers every time I do something. You know, these are the kind of things you need to check out and debug the code when it's giving you troubles. Make sure you're feeding the right variables into your right functions. If you're doing the POW function, it takes some doubles. So I had one student who had 1 divided by 3 to get a 1/3. Well, it read both that 1 and the 3 as an integer. You should have done 1.0 divided by 3.0, and then it works. Stuff like that. Okay, so let's go ahead and look at the code. So this is my final code. So what did I change here? Well, since we had the case where we had a trimer, I added this here, the number of absorbing spheres. And that goes to initialization. My end time here was 30,001. I played with that. Like I showed on the spreadsheet, the graph, I set that to 6 for my absorbing radius. Sim space is 200. My infinity zone, pseudo-infinity zone, is 99% of my R. To reduce noise, I did my D of R for my shells to 2. I changed my definition of the pi to this. That way it gives you many decimal points as you need to double. And it's really compact. And the length of my concentration array is the same. Now this is my function list. So you see I'm doing a lot of functions. Initialization, radius calculation. So I just give it 2 points, x, y, z, give me the radius, that's important. The absorption check, so I give it an x, y, z of a random walker, and then I give it the x, y, z array of my absorbing spheres, and it's going to check each one to see if it's absorbed. Move walker, that's going to give me a delta x, delta y, and delta z. I feed it into this array. That's how I move my walkers. Recast, I give it, I just pass the arrays x, y, z for the walkers, and then just give it I for the ith walker, and it'll recast it in the pseudo-infinity zone. Same thing for periodic boundary condition, except now I give it a radius. That's the actual radius of the walker. So from that I can calculate where I need to move it, and then, of course, concentration. I also had trouble here. Another thing is, if you made the system too big and your absorbing sphere too smaller, the built-in random number generator would fail. What I mean by that is, like I had a case where I had a simulation space of 500, and I used the code that we did to initialize it in 3 dimensions spherically, where you do the random number to the 1/3 power times R. Well, when I use the built-in random number generator, the lowest, besides 0, the lowest radius to get me would be 15. Between 0 and 15, there was this big gap. That was because the resolution of the random number generator from 0 to 1 was just too big. And then when I recast that to bigger space, there was gaps in the small r's. So I use this function here, PSDRAN. It's a better random number generator. It's based on one of the numeric recipes. I will give you this code in a text file on Canvas. it works essentially the same. It just produces random numbers between 0 and 1. And it's a function like this, and you just give it the seed values, whatever the seed is. Okay, so let's go with the function. So here are all my arrays. Here are all my variables here. All the variables in the main are right here. This buffer is just going to be a string that holds file names. I don't even need this here because I'm using a different random number generator, but if you were using the built-in, you would call this to initialize your random numbers. Make sure. I commented out here. Oh, well, I have comments around the section where I actually allocate and set all my arrays. So I allocate all the big arrays. I set to 0 all the arrays that I'm using. So here's the arrays for XYZ of the walkers, XYZ of the absorbent spheres. I zero out my concentration, and then current versus time is another array that I use. I initialize the system, set us all up, set my current to 0 here, so this will be a cumulative current, not current at every time step. I have a for loop here. I just minimized this one with I. I have a for loop that goes over t. It starts at 0 in some time, so this is my time loop. And then at every time, I fill in what the current value is, how many walkers were absorbed in that time, and I record my concentration. And that's what I'm doing with this if statement, is recording the concentration. So I only want to do certain times. So if t is divisible by 500, it'll record up until time 1,000. So 1,000. So I'll get 2 concentration measurements at 500 and 1,000. I also want to do it if it's every 1,000 steps. So after 1,000, I'll have 2,000, 3,000, 4,000 in my simulation. And then I want an initial one. So I want one at a time. So this is and. This is an and statement. This is how you do or. So it's what we're doing here is this condition's met, or this condition's met, or this condition's met. And if any of these 3 conditions met, it'll do what's in this if statement, which is measure the concentration, print the concentration. And then after everything's done, it's going to print the current array versus, so that's current versus time. Okay, now let's look at in detail. First thing is initialization. So we'll come here and look at that. So right now it's set up for 1 walker, and I go ahead and just set that to 0 XYZ. If I were doing the trimer that was the open configuration, I would use this for my Z, and I would set this in __a to 3. So that's how I initialize my random, absorbing spheres. Now I need to initialize my random walkers. So I need to do 1 random number between 0 and 1. This is how you use the PSD_rand function. Just give it the seed. And then I just say, okay, let's do the 3rd power of that random number times r, which is the outer bounds of our simulation space. That'll give me my random r. And then random theta and phi. So another random number from the random theta, random phi, phi. And then I just say, what's my x, y, and z? Then this is, you see, this is all in the do while. It's going to say, hey, was that walker I just initialized in one of the absorbing spheres? If that returns a 1, which means yes, that random walker is in an absorbing sphere, it'll just recast it. It'll go, oh, let's just re-roll that random walker. And then it does the check again. It says, okay, so I throw a random walker, it's in one of my absorbing spheres, it says 1. This function returns 1. I do it again, it's not in my absorbing spheres. That means this function will return 0, breaks out of the do while, and goes to the next random walker. That's it for my initialization. I initialize my absorbing spheres, I initialize my random walkers, and that's all I have to do here. And look, I'm using my functions. You can call functions within functions. There's nothing wrong with that. Okay, back to the main. System is initialized. Let's run through the first time step. So one, we want to move the walker. I'm just following along with my plan we made last video. Okay, how do I move the walker? It takes in this array with 3 variables, and in the first spot it puts the dx, in the second spot dy, third spot dz, and it just says, okay, the ith walker is just its position plus dx. So how do I do that? Let's go to that function. And that function is just pretty simple. Just get a random number, get a random theta, random phi, and do what we've done before with the 2D assignment. So walkers are moved. Boom. Okay, we've moved that walker. The ith walker's been moved. 2, we need to check, see if we hit anything. This is where the absorption. So I want it to return 1 if it is absorbed, if it hits the absorber, because then I can just use that value for my change in current. My current goes up by 1 if it's absorbed, so di. I call it the change in current. So let's look at what we're doing here. Absorbing check. Okay. Not much going on here. We have an outer loop here that goes through each one of the aggregates, the monomers in the aggregate. We have a calculation. We calculate the radius between our random walker, the ith random walker, given by x, y, z, and the ith monomer of the aggregate. That's all we do. If that radius is less than or equal to a, that is, that infinitesimal small walker vapor is on or in one of these absorbing spheres, we set this j equal to 1, it's initialized to 0, and then returns j. So if nothing happened, if it wasn't in one of those walkers, it returns 0. If not, it returns 1. So we have absorption, it returns 1. And that just goes into our change in current, or di. Okay, so that just checked for absorption. Now we need to say, okay, we need to recast the walker if it's absorbed. So if that di equals 1, means that walker got absorbed, it's inside or on the surface of an absorbing sphere, well, I would equal I plus di plus the 1. And then we need to recast it. Now I give it the x, y, z arrays of my walkers and the ith one. So that tells you which walker needs to be recast. Let's look at how we do that. We use the recast function. And all we're doing here is saying, okay, give me a random number. The range I'm going to cast it is between r and the r infinity zone. So this is the range I'm going to cast it. Take the cube root of that random walker. This is the exact same as doing power random number to the third power. This is just a cube root function that's built in. So random number goes in there. So if I do this times this, this gives me a random number between this delta r here. And then you add r infinity to it, and then you will have this r, random r, between r infinity and r. And this is for debugging. This was just an error statement, just in case. I was wanting to make sure this random number generator didn't do anything weird. If it did anything weird, well, my random number could be greater than 1 or less than 0. Which brings me to the point. Caution when you're with your seeds with this particular version of a random number. Don't make them gargantuan. Something in the 100,000s and millions is good, not the billions and trillions. You might cause, if you make your seed too big, you may cause an error. So that's the caveat of working with this random number generator. Again, I'll include this code in a file on campus. Okay, so I got my random R in the zone I want it to be. Right? Give it the range, and then you add that R infinity. And then, of course, random theta, random phi, just give it a new coordinates. So recast is easy. Putting in the pseudo-infinity zone is pretty easy. Okay, now here's another thing that can save time. We only need to do one of these. Like if it's absorbed, we don't need to do an out of bounds check, right? Because it's obviously in the center of the system. If it's not absorbed, then that's only when it's possible that the random walk went out of bounds. So that's why I have this if-else statement. So if it is absorbed, then you just do this. Else, it's not absorbed, then let's actually measure the radius between our random walker and the center of the system. We'll call that our periodic boundary condition. If that radius, which is the radius of our walker, in the center of the system, is greater than our bounds, then we need to do periodic boundary check. Maybe I should just look over how to do this R calculation real quick. It's pretty simple. It's just a simple, you have XYZ, XYZ, the difference squared, right? X minus X1 squared, Y minus Y2 squared. Actually, let's fix this here. 2. This is just for my, for me, this doesn't change anything. I called X1 and then Y2 and Z2. It should be X and then X2. Just a little detail that does not matter at all, but it bothered me. So you have your delta X squared plus delta Y squared plus delta Z squared. Take the square root of that. That's your rate. It's simple. But I'm going to use this a lot, so do it in a function. Okay, now periodic boundary condition. So this is actually spherical periodic boundary condition. I didn't do any weird recasting. And let's go over that for a bit. The logic on that one. So here's my pin. Here it is. So here's my spherical space. Here's the center. That's 0, 0. And then that's right there. This is our periodic boundary condition, this whole thing. And this here is our distance we went over. So what we want to do is we want to actually be over here, where this is our distance. So what we're going to want to do is we're going to want to, so this R, let's look at the vector form. So this has a vector. See? That way. So what we want to do is we want to move, we want to move the unit vector, the opposite of the P boundary condition. So we want to go the opposite way of this, and we want to go this distance here. We want to go this direction, this is our direction, and this is the distance, the magnitude of that direction. So what is that magnitude? What is that direction? Well, this is R, big R, right? Minus that distance here. That distance there is R PBC minus R, right? That's what this is. It's the same thing here. So that distance is then 2R minus R. See, these are all scalars right now, right? And we're going to move what direction? Well, we're going to use minus the direction of that walker from the center. So, right, it has this vector, and we're going to unitize that vector. Well, what's that? Unitize that vector, so what's that equal? That equals, well, let's do the, here, let's bring that in. So it would be R, you see all I'm doing is move the minus sign, minus 2R, and then we bring an R, periodic boundary condition, and then R. See, so I want this unit vector, made it non-unit, and we end up with this here. So this is a scalar, it's just a number. Get my pin back here. So then our final answer is a scaling factor of 1 minus 2r r. Oops. All we're doing is a little vector math here. So that's going to be our new position, the ith walker's new position. So this scalar here, and you see this is going to be greater than 1, right? Because this is bigger than one of these, but it's only slightly bigger, so 2 times that's definitely going to be bigger than 1. So it's going to be very close to -1, a little less than -1, right? So we have 1, and you can tell that from above here, right? So this is 1, this is going to be less than 1. It can't be it won't be bigger than 2. So what's this mean then? So that means x I new equals this x I, its current position. So let's look at that in code. And that's it. This is all the code it is. So I have that factor there, that 1 minus 2 times r of the radius that we put in. And then I just multiply my current position by that r, and that's my new positions. And so that's why you see why I have to input the I here. The I goes in here because it's the ith walker. And I just put these in here because I can change rays inside functions. So anything I change with the ray will stay changed. So periodic boundary conditions, pretty simple. So that's it. That's the entire population of walkers moved one time step. This is this entire for loop. Move the walker, get the delta x, delta y, delta z, move the walker, check absorption. If absorption happens, increment your current, recast the walker. If not, check to see if it's out of bounds. If it's out of bounds, use periodic boundary conditions to fix it, to put it in bounds. So I'm going to minimize that for loop. No, that's that for loop. And current is just how many walkers have been absorbed total. And it goes at time t. So it takes time t, it says how many have I absorbed so far, and I can graph that. And then like I said here, if time is in one of these conditions, we measure concentration. So let's look at that. That's the final thing. So length is defined already here, this constant, just our length of our system divided by our dr. So we put all those to 0. Then I'm going to go through every single walker in the system. I'm going to calculate its distance from 0, from the center, and then that bin that walker is its radius divided by the delta r. And this is an integer, so this has always been an integer. This is an error check. If that bin is greater than or equal to the length, then that would be out of bounds of the array, the concentration, C array. So that's bad. Now you could get, so let's instead of just print an error statement, just say, hey, bad thing happened. Because this will cause a crash if this happens. I've seen where we're debugging where this happened, and we're like, oh, what's wrong here? It's with this concentration, but really the problem is with the initialization. The problem is with the walker movement or something else. So just to let you know, hey, this error happened because the bin was too big, which means the radius was too big, which means somehow a walker goes out of bounds. So all we're doing then is just counting how many walkers are in each shell. Once that's done, we go over here and divide each shell by its volume. So I have this volume variable, which is 4 pi. This is our r squared. Our r is I times dr, and then we're going to be halfway through the shell, not on the edge of the shell, which is why we have half dr here, We square our R, times it by dr, let's divide the shell, divide each shell by its volume, and that's how we find concentration. And then I print this with this print array function. So I use this s printf. So printf prints to the console. Fprintf prints to the file. Sprintf prints to the string. A string is like an array of characters. So this says, okay, this array of characters, you put this text in here. You treat it just the same. Use the %d for an integer, so this would be c concentration at time t dot text. And you do that, you run the simulation, and oh, that's not the simulation. Here's the simulation. So I stopped it at 6,000, but this is these files here. See, time at 0, and just give me files like this. I don't have R here. I just have I, so I'd have to multiply by the 2R, and then you can graph your results and get this. So I have at time 0 to 6,000. I stopped the simulation because it seemed to be pretty steady state. This little gap here, it's going. I mean, it's reaching its C infinity, and it looks like I could have let it gone all night. Maybe it would reach here, but there's no way it could actually 100% match because there's a gap here at the edge of the system. This gap here is what's probably going to cause a lot of the problems. I adjusted so this is the I, this is the index, so I adjusted the sheet. I just multiplied by 2 or whatever, inputted the data for each column. And this is all, the black lines are the theoretical. And you say even with 5 million at 200 size system, you still get a little noise at the front end here. That's okay. So let's take a look at the print array. I think I have a video on this. I think I put that code out there. You just have the file output before. The only thing is now you should have this character array, and instead of putting a name for our file in quotes, we just put that character array variable there, and it takes it, and everything else is the same. And that's it. Yeah, let's run it. I'm going to run it without debugging. That is a little faster. And this is pretty big, but you see how slow it is. And let's look at the task manager. Let's bring that in. So it's not even beating Chrome right now. You can see we're only using like 1/3 of a gig of RAM. Most modern systems, most of your laptops should have like 4 gigs. I have like 8 gigs. 4 or 8 gigs is pretty common. 16, something like that. So if you're memory-wise, it should be fine. It's not even using that much CPU. So you can get, I could probably do 10 million, 20 million, 30 million random walkers pretty easily. It's just going to take a while because it can only use one thread of the CPU. Well, that's where it's using the CPU right there. So this is that. There it is right there. And the rest, this is, so this plus this is how much memory it is. So it uses about, okay, let's say it uses about half a gig of memory. And it takes entirely one core. So I haven't even reached 1,000 time steps. I can't pause it to show you. Remember, I time here, I write stuff to the screen to let me know where I'm at in the simulation. So it should do it at 500, 0, 500, 1,000, 1,000 after that. But I'm not going to run that anymore. So that's how the simulation is done. If you had a lot of trouble with it, look at the code, understand it, because really this next assignment is just a modification of this code. You're going to use a lot of the same functions, you're just going to use them in different ways or modify them. Because we're going to be able to aggregate now instead of absorb. I will post this as a file. I will also post this will include this random number generator. How do you use that? Well, don't worry about what the function is. Don't worry about any of this. Just copy and paste it. Just leave it, and then every time, and then have, of course, define it. And then the way you call it is just every time you call it, it's just this statement here. PSDRAM. Give it a seed, and it'll give you a nice random number, 0 to 1. And remember to keep your seed a reasonable length. 100,000s in the millions, not millions or trillions. Okay, I think I've rambled on enough. See you in class Tuesday.